Hello, hello everyone. Welcome. Today we're gonna be talking about an intro to virtual reality in Unity with Thulasi, and she's just gonna be walking you some of the basics. Once again, you don't need much experience to attend this workshop, so keep that in mind. And so I'm just gonna hand it over to her, and she's gonna walk you through an amazing hour on virtual reality.
Thanks, Meena. Hello, everyone. I'm Tulsi. So I'm a Unity developer, having worked on a couple of VR projects for Hasbro and Shaking Earth Digital for PC, Android, and console platforms. So today we will walk you through just like basic VR setup for Unity Cardboard using Google VR SDK. I'll try to keep the coding like really simple and talk about a couple of like best practices, optimization, and just VR, moving in VR using just the camera. You can use Android or iOS. Uh, I'll start sharing my screen now. So I'm going to be using 2019.4. Make sure you have an Android build support, or if you prefer using iOS, just go to your installs, select the Unity you want, and go to Add Modules. And you will have a couple of options for Android or iOS. So I'm going to be building an APK, so I'm sticking to Android. And let's go and create a new project. Make sure it's 3D, and we will call it VR Demo Cardboard. And for the Google VR SDK, you will need this package. I will be sharing the link here. So you want to download the Google VR for Unity Unity package. So Unity package, it's just a zip file, and it contains the project assets, which we will be making use of. And before you import all the assets, let's go and change the platform to Android. So when you do it before you import all the assets, it's so much faster. When you import assets and then switch platforms, it takes a while to like convert all the assets to Android. So let's switch to Android first thing. And I will be importing the Google VR SDK we just downloaded. And I have set up a Unity scene with some assets. And I will be sharing the package for that too. So you want all the files in the Google VR. Google VR SDK has a couple of useful prefabs like the editor emulator. That prefab is really useful to see what the VR view is like in editor, so you don't have to build an APK every time you make changes. And also like a Reticle prefab, Raycaster. So yeah, we've got the Google VR imported, and I'm going to import the custom VR starter package, which I just shared. So I've got some assets downloaded from Asset Store. There are plenty of free assets and scenes set up for us. So yeah, it's so much easier to like use those.
Hey, I don't think your screen is showing.
Sorry, what?
I don't think your screen is showing.
It says it's sharing window. Let me try again.
All right.
How
Perfect.
about, okay, cool. So let me go over again. So I've imported the Google VR and the VR demo starter packages. So I'll give you a couple of seconds to import those two. So once you're done importing the starter package, go to Scenes and open the VR demo scene. So here I have a RPG landscape with a couple of buildings, huts, and pathways. And we have a main camera set up here. So when you hit play, you will be able to see the camera position. Now, to be able to see the VR view, let's go to Google VR folder, prefabs, and drag the editor emulator into the scene. So if you look at the component there, it says Alt plus move mouse will let you like look around beyond pitch, and then change role, which is just on your x-axis. When you hit play, now when you press Alt and move your mouse, you can see what the VR camera will be like. So you can also notice that the camera view has like dropped to 0. When you go to main camera and see the transform, it's at 0. That's because VR camera would adjust to world origin, and the Y position will relate to your headset, where your headset is, if you're seated or if you're standing. But we want our camera to be here. So let's create a camera rig and let that hold the main camera. So go to main camera, copy the main camera's position, and select the camera rig and paste the values. Now the camera and the main camera rig, they will be in the same position. Now what we want is to hold the main camera. So drag the main camera under the camera rig, and you can see it's at 0 local position. And now when you hit play, you should have the right position. So now you can just like move the camera rig anywhere you'd like without having to worry about the VR camera position. So to talk about moving in VR, since we won't be having a mouse or a keyboard or even controllers like in cardboard, we will be making use of just the camera and teleport to different waypoints. So we will be using raycasting, meaning we would gaze at an object and then get the player to teleport to that position. So we can do that by using a reticle pointer. It's just a cursor. Just think of it as a mouse cursor in 3D world space. So when you go to the Google VR prefabs, go to cardboard and drag the reticle pointer. That should be under the main camera. And now when you hit play, you should be able to see the reticle. Can't see it. I think that's because we don't have an event system. So the next thing we want is an event system. Drag the GVR event system to the hierarchy. Event system in Unity, if you don't already know, handles all the input processes, then interactions with physics and also graphics. So the Google VR event system has an event system component and the input module, which is different from the standard input module because we have like VR, and instead of using the mouse cursor, we will be having a Raycast reticle in the world space. So once you have this in the scene, add a Raycaster. This is again a Google VR component. So you want the physics Raycaster. Physics Raycaster because we will be using 3D objects to move around. If you want to use graphic Raycaster, use it for like canvas, UI, like button clicks and scroll slider, etc. All right, just checking. And so now to set up the project to be working in VR, let's go to File, Edit, Project Settings, and Player. So in older Unity, we would go to XR settings and enable virtual reality supported, which is okay for now, like for Google VR. But if you're in 2018 plus and want to develop for Oculus or Steam VR, you want to use the XR plugin management. But for now, VR SDK is totally fine. So when you enable that, add an SDK cardboard. So that will just add a package for Google VR. Cool. All right. So in the scene, I have a waypoint prefab. So it's just a birdhouse, bird post, and we will be using this as a waypoint prefab and have it spread out in the landscape to teleport to each birdhouse. So you will see that the bird waypoint prefab has a box collider component, and it has the is trigger enabled. So what is trigger does is when any interaction happens with the birdhouse, it will send an event trigger, and we will be adding a function to teleport whenever the user gazes at the waypoint. So we will be gazing using the Reticle Pointer. So to explain Raycast, I have an image here. So think of Raycast as just a vector that's been cast from a point of origin. In our case, it's the camera. And ray distance is how far do you want to cast the vector to look for objects to hit on. So in our case, it's our waypoint prefab. And since this is a pretty big landscape, we want the raycast distance to be around like 100 meters. So let's keep it as 100. So you want to select the GVR Reticle Pointer, and under the GVR Reticle Pointer component, change the distance to 100. I'm not sure why I can't see the reticle. There it is. It is kind of offset, so I'm going to reset it. It should be under the main camera and reset to origin. So now you can see the reticle. So what we want is to be able to gaze at this birdhouse and then teleport there. Now, select the waypoint prefab and add an event trigger. Event trigger component has different event types like pointer exit, down, up, and click, which translates to touch events on your Android or iOS devices. So we want to gaze at the waypoint and tap, which will be click, and then teleport. Because you don't want to just like look at an object and then start teleporting. And also, let's start adding the teleport script now. So on the waypoint prefab, add a new script called teleport. I'm going to open the Visual Studio Code using this option. For some reason, this loads up the plugins. So I have started an update. Let's add a function called onReticle flipped. There. So this is where you want to teleport there. And for that, we want our player position. So let's create a game object called player. And in start, let's assign game object dot. We can use find game object with tag. We can also make this a serialized field and use it on the add a property on the inspector. This is just another option. Now, what we want to do is once you click on the waypoint, you want the player position to be the waypoint's position. So that would be this transform.position. We don't want updates, so I'm going to delete that. Can you see my screen? How about now? Weird. All right. Can you guys see it now? All right, there it is. Sorry about that. So we added the teleport script. Now let's see if that works. No, it won't, because let's go to the waypoint prefab. On the event trigger, we want to add a function that says, hey, when there is a click or a tap, let's teleport. So under event trigger, add a new event. So our script is attached to the waypoint prefab itself, so drag that here. And the function is under teleport.cs, and it's called on reticle clicked. Now let's try that. So now when you gaze at the waypoint, do you see the reticle moving? And now when you click, the player's no exception. The player is not assigned here because we don't have the tag set to the camera rig. So let's fix that. So there is an inbuilt like tag called player. So let's just change that and try again. Now you see the player is at the waypoint's position. We don't want to change the height of the player, so we want to preserve the Y position. So let's fix that by creating a new vector, keeping the transform of the waypoint, just using the X and Z. And for Y, we want the player.transform. Z. Now that's so much better. So that's teleporting. And you can also just duplicate the prefabs, spread it out. And play around. So having a teleportation and moving the player abruptly is not really perfect. So we want something more smoother. So we can fade in and fade out the teleportation itself. There is a fade canvas object in the VR demo scene. Enable that, and you will see a black image. It's just a full black image, which is going to be attached to our camera. So select fade canvas and use your main camera as the render camera, so the image follows the camera around. Now when you select the image, you will see it's really close to the camera. That's because we have set the distance at 0.1. So what we want to do is to fade in and fade out. It's just a simple trick. Have a black image and get its color component and just slide the alpha value from 0 to 1. So that's fade in and fade out. And the fade canvas should have a fade script attached to it. When you open that, you will see there's a fade image. That's the black image, and an alpha value 0. So we will be modifying the alpha value from 0 to 1 for fade in and 1 to 0 for fade out. So I have two coroutines here. I'm using coroutines because we want to increment and decrement the alpha values over a couple of frames. If you use a function as like public void fade in and use a while loop to increment the alpha value, that will happen in a single frame. we want the transition to be smooth, so we're using a coroutine. What coroutines do is it will execute the while loop till here, yields in the current frame, and waits till the next frame. So every frame we're incrementing the alpha by time.delta time, which is about like 0.03 to 0.01 or something in that range, depending on your frame rate. So let's go back to teleport and do fade in first. So to call coroutines, you should be using start coroutine. And you want the fade script instance and fade in. And then once the player moves, we want fade out. Let's try that now. All right, so you want to start with the image color alpha with 0. Otherwise, you'll just have a black screen. So now you see you can't like interact with the waypoint. That's because you have an image right in front of the camera, and the camera is actually raycasting, the reticle is falling on the image, and it's getting blocked. So select the image and disable Raycast target. We don't want to interact with the image at all. Now you're able to gaze. So you didn't really see the fade. That's because we are calling a coroutine in a function. A function doesn't wait for a coroutine to finish. It just kicks off a coroutine. So it fades in, moves a player, and starts fade out. So by the time it calls fade out, fade in hasn't really finished. So to fix that, we want another coroutine. We'll call it start fade. So here, let's wait for the fade in to finish by using yield return and start coroutine. And then you want the rest of the code. So under on reticle click, start the coroutine, start fade. So now you should be able to see the fade. And you can also see the alpha changing from 0 to 1. So that's more standard to use fade in and fade out for teleportation. You can also play around with the speed of the fade by multiplying the time.delta time by some factor. Let's say 2. Or it can be lower, 0.5 or 0.1 if you want a slower fade. That's so much faster. So that's waypoints and teleportation using Google VR. And the other movement technique we're going to do is just flying, just because flying is so much fun in VR. And the Cardboard app has a demo game that just like lets you play around with a bunch of birds. And we can try that here. So let's copy the scene and save it as a new scene. We'll call it VR Demo Fly. We don't want any of the prefabs, so we'll delete those. So we have the camera rig, event system, editor, emulator. To the camera, let's add a script called fly, or just fly script. So when you're adding new scripts here, it's good practice to just move the new scripts to a scripts folder, just because it's cleaner. So let's open the fly script. And for fly, all you really want is the player position, which is the script is already attached to the player. So you want just transform dot position plus equals. So flying would be in the direction that the camera is facing. So that would be camera.main. Camera.main will fetch you the game object that's tagged as main camera. In this case, it's the main camera. So you want the forward for camera.main. And again, multiply that by time.delta time, because forward is a unit vector. If you don't add time.delta time, it would, every frame, you would be moving 1 meter per second. So 1 meter per frame, we really don't want that. So this is all we really need. So now if you look anywhere, you will be floating in that direction. We could make it a little bit faster. So let's add a private float speed factor. So I'm just showing you different ways to add inspector variables. You don't always have to use public to be able to see the variables in the inspector. You can add a tag called serialize field. So this will show up in the inspector when you add that. And you can edit the speed here to, let's say, 5. And you want to multiply the speed to our position. So that's so much faster. So again, like how we saw the colliders and event triggers, you can use those to trigger flight. You can use pointer click twice to just on an object, like, or a button to start flying, or you can have a starting position, like an empty transform. And then when you maybe click on the terrain, you can land. So yeah, you can play around with the colliders and event triggers for different game mechanics. So that's really the flight scene. Let me see if you guys have any questions. Okay. So now to talk about optimization, let's go back to the waypoint scene. So we have a lot of objects here, and luckily they're all like low poly, and they're all sharing one same material. So if you click on any object, it's just using RPG-PP mat. That's because they've baked all the textures into one image. So that's really great for optimizing, reducing the number of draw calls for VR. And another way to help with like processing power is by baking lights. Baking lights is basically just pre-calculating the brightness levels of the scene so that Unity, the game doesn't have to do it in real time when the game is happening. So in this scene, we have one direction light and it's at real time. So let's change that to mixed. And we also have so many static objects here. We will not be moving the house or the tree or the rocks. So we can change all these objects to, except for the sky. We'll disable the sky. We'll change our static objects to static by checking the static keyword here and change. Now go to Window, Rendering and Lighting Settings. I have auto generate. I'm going to cancel that. So when you enable mixed lighting in the direction light and convert your objects to static objects, Unity starts saving those, saving the baked information into light maps. So under lighting settings, you want to disable the real-time global illumination because we're not doing any real-time calculation. We're doing mixed lighting. Mixed lighting is just having point lights, direction lights. So once you have that enabled, you have some light map settings. So light maps are just textures where Unity will write all the brightness levels for the whole scene. And then it goes on to the build folder into the resources. And then without having to do any real-time calculation, it just uses like the cached light information. So for the workshop, I'm going to reduce the light map resolution so the baking time takes less time. And I'm going to generate lighting. One more thing is I'm going to change the light mapper to progressive CPU because that's way faster. And then generate lighting. So you can see the changes here. Unity starts storing them to bake light maps. If you click on bake light maps, you can see how it's writing them to the textures. And in our light map settings, I've set the light map size to 1024. So the texture size would be 1024 by 1024. You can have it bigger, so we will have less number of light maps, but it will take longer because it has to put all the lighting information into like one texture. So once it's done baking, it saves it to scene folder. It has created a VR demo folder and saves all the lighting data in that. So that's kind of like caching your lighting information. So Another way to profile your scene is by using the stats window in the game. So when you hit play, you will see how many batches. Batches are like dynamic draw calls. So how many draw calls does Unity make while running the game? And saved by batching is 227, which is good because we have baked a lot of lighting data and we have made all the meshes static. So Unity combines similar meshes to one draw call. So if we don't have them as static, you will see a lot of batches. And one of the best practices for mobile VR is to keep the number of draw calls under 100 or 50 even sometimes. And the number of triangles, if it's under 100K, that's perfect. So yeah, this window is super helpful to see which frame is causing a lot of issues. For example, this frame has over 100K. That's because we have a lot of things going on there. And another window that's helpful is the profiler. If you go to analysis and profiler, it has a lot of information on CPU usage, rendering, which is the GPU side. When you click on a frame, you can also see those spikes here and just like analyze what's going on there. You can see the CPU usage, and this is all just C# scripts or Unity's in both scripts, all that. So we're at a pretty good frame rate here. And if you see rendering, you can see even more depth, like draw calls. That frame has a lot more draw calls compared to other frames. So if you pause there and go to rendering, you can see the draw calls is just 46. We're doing a lot of batching. We're not doing any instancing because we're really using just one material. Instancing will also combine similar meshes. Like if you have a game with a lot of like trees and a lot of buildings that look alike, you can use GPU instancing. You can enable instancing by going to the material of an object and enable GPU instancing. So that will combine similar meshes, even if you have different colors or different properties. So we've got the light baked, and we can also compare this to our other scene with the same objects, but no baking or no baked lighting or no static objects. So if you go there and hit play and look at our game stats, it has a lot of like batches, and we have 0 draw calls that's being saved by batching. So that will be calculated in real time, and as your game gets bigger, it's not really like a good practice. So it's always better to have less number of draw calls and more number of like batched objects. I'm going back to VR demo and let's build this game. Go to your project settings and under player, change your company name or demo product name. And in other settings, you will be able to see the package name. So in Android, if you go into the Android root folder and look at the data folder, you will see a couple of folders named as com.whatever.app name. So these are unique identifiers for each Android application. So we'll leave it at this and then just build our scene. Go to File, Build Settings, and add Open Scene. Then build. So I already have an APK, so I'm going to use that. So the first time build takes a little longer, and then once that's done, it's much faster. There's a couple of other links that are useful to get started with Android and Google VR for Unity. I will share that. And then if you want, I also have a repository on GitHub that you can download and take a look at all the scripts. It's pretty much the same thing that we developed, but it's two different scenes and different assets, and it's has both landing and flying scripts attached to it. The build is taking a while, so if you have any questions while we wait for the build. So my APK is ready, and if you have Android platform tools download on your computer and set it up, you can use command line to install your APK, which is Android package, and or you can transfer the APK file to your phone, and when you open the APK file, Android gives you an option to just install the app. So I have my phone connected to my computer, and I'm going to install this vrdemo.apk. I will try to show my phone screen once it's being downloaded. So since this is a VR project, I will have like two different screens attached to it. And this is the flying script. So yeah. And if you have a cardboard, perfect. Like you just have to hook up your phone to the cardboard and be able to view. So yeah, that's all I've got. If there are any questions. Cool.
Feel free to ask any questions if you have any. And while we give some time for that, I just wanted to quickly go over the workshops we have today and tomorrow in case you're interested in those. Today we have an intro to visual design with Emil Polyak at 5 p.m. PST. And tomorrow we have a ton of workshops, such as creating game interactions for Unity, a webinar on Skyscraper Games Trilogy, and Entity AI. So if any of those topics seem interesting to you, make sure to tune in today and tomorrow and check out our calendar for the times. If anybody doesn't have any other questions, any last words? Thulasi?
Oh, yeah. No, that's it.
Okay, well, if you joined us, thank you so much for tuning in. And if you have any questions, hop on over to the Discord channel and either me or Tulsi would be happy to help you. And thank you so much for tuning in. We hope to see you around. Oh, we have a question.
Cool.
Go ahead.
Oculus has two platforms, PC, which is for the Oculus Rift, and Oculus Quest, which is Android. Oculus also has 6 degrees of freedom, meaning you can walk around. You can also have your head rotation, but Google Cardboard just has head rotation and no position tracking. If that answers your question.
Well, I hope that answers your question. When you code.
You have external, like extra other factors like adding hand controllers and also keeping in mind of like the whole VR space because the players will be moving around. But just like Google VR SDK, Oculus also provides a Unity integration with a lot of like demo and samples. So it's slightly more difficult when you are coding for hand controllers and avatars, but for simple experiences, you can just, do without any other like extra controllers, just headset. And SteamVR is also kind of similar to Oculus, left and right controllers and camera rig. Oculus 2, as far as I know, the resolution is higher. GPU, I'm not sure. Everything else is pretty much the same except like for the resolution and field of view is the same, and it has a softer, I think, headset. Yeah, because again, it's an Android platform for Quest. So it's just think of it as another Android device. So it it's just slightly better than cardboard devices, like phone devices. So yeah, always like try to stick to 100 raw calls because you never know, you might need more memory for on the CPU side. So Oculus has a OVR overlay, so inbuilt. So when you go to the Oculus Home in the Quest, you can enable the overlay. So it's kind of like the game stats that we saw. So it has a graph for like the frame rates or any spikes, number of draw calls, and even the temperature of the device, I believe. Yeah. There's also another PC Oculus tool. I don't remember the name, which is really similar to the profiler and the frame debugger combined. So, yeah. Rift test is just Quest, but it's like tethered to your computer. So you're not really restricted by the number of draw calls because if your PC is going to be powerful if it's supporting VR. So it's not very hard to develop for Rift S and Rift. Oculus Oculus Link is a cable that when you buy Quest, they provide a cable called Link. So when you connect your Quest to your PC, it just you can enable and use Oculus Rift. So you're basically just making use of your PC power, but on Quest. So it's like converting your Quest to Oculus Rift. Rift S is just something they like released before Quest, so I think they stopped selling those because Quest and Link is pretty much the same. No, when Quest Link is connected, you are on PC platform. So you will be building different applications. Like for PC will be a Unity executable, and for Android it's APK. So it's just like virtual computing. Cool.
Awesome. Well, thank you so much for all the great questions, and thank you, Dulcie, for answering them. And so I think we're gonna call it. Thank you so much for presenting your workshop on VR. I'm sure a lot of us who are beginners have learned a lot from you. And if you were an attendee, thank you so much for coming, and we hope to see you around soon. Bye, everyone.
Thank you. Bye.